In part 2 we're going to look at Ohm's law and resistance. So here we go. We've talked about current and voltage. The question is there any relationship between the two? And Ohm is credited with his law where he just got a metallic resistor, which is shown like this. This is the symbol for resistance. And he passed a current through the metallic resistance, and he measured the voltage across the metallic resistor, and he found that it was an incredibly simple relationship between the two. He found that if you double the voltage, then you double the current, and we know what that graph looks like. It's a straight line through the origin. Voltage is in volts, the current is in amps. And so then he said, well, let's define the gradient as equal to the resistance of the unknown metallic conductor, and it has the symbol R. So here we go. Here's his formula. Resistance equals the ratio of voltage to current, and in symbols, R equals V over I. And now in red come the units. Well, on the left-hand side, we've got 1 volt per amp, and that is known as 1 ohm. And it's given the symbol capital omega. This is a Greek letter. It's rather beautiful, really. And there you have it. That is Ohm's law. So, for instance, if I look at my graph here, and I find that when the current is 2 amps, the voltage is 3 volts, then R equals 3 volts divided by 2 amps is 1.5 ohms. Now, even Ohm recognized that this relationship had some limitations, and so what he said was, for a metallic conductor, okay, so we're not talking about glass or wood, for a metallic conductor, and then he said at constant temperature, because he spotted straight away that actually if the temperature changes, then the graph isn't straight anymore. But if it's a constant temperature, then V is proportional to I, as shown by the graph. So there you have it. That's Ohm's law. If you know V and R, you can write R on the side of the metallic conductor, also known as the resistor. But if you know V and you know I, you can find R. If you know R and V, you can find I. If you know I and R, you can find V for any resistor in a circuit. So that's Ohm's law. Now, we have, however, got lamps with hot filaments. So what about if the temperature does change? And if the temperature does change, the electrons find it harder to get past the atoms because they're jiggling around so violently. So if the temperature does increase, then the resistance increases. Now we can show that in a graph. The line is no longer straight. So here it comes. Let's just move things up a bit. If the temperature does increase, then the resistance increases. So here's a picture. We've got the same voltage against current on the axes, but you find that after initially quite straight line, it starts to go up like that. And this shows that the resistance is increasing as it gets hotter. So what's happening is that the current is causing the filament of a light bulb to get hot. Because that's what we want with a filament light bulb. They've largely been replaced these days by LEDs, which are much more efficient. In other words, they give out a lot more light for every joule of energy that's given to them. Unfortunately, a filament light bulb gives out mostly heat. So, but this is the graph for a lamp, a hot filament lamp, also known as light bulb. Let's call it a light bulb. So that's one weird thing. It's not particularly weird, but we come across them all the time. That doesn't obey Ohm's law, but it's not a metallic conductor, and it's not it is a metallic conductor, but it's not at constant temperature, is what I should say. And we've got one other funny thing to have a look at, and this is called a diode. Now, it isn't a metallic conductor, it's a semiconductor material. And the thing about a diode is the current can only pass one way. So it acts like a sort of one-way valve. It's really important for converting AC into DC. So its graph is very peculiar. Have voltage against current, but this time we need to show the reverse direction as well as the forwards direction. And to be able to see this graph, I need to have a different color. If the voltage is going backwards, then unfortunately the current stays zero all the time. So there it is. That's the current is zero. But when the voltage goes forwards, it gets to about 0.7 volts, and then suddenly, whoa, it goes like that. It usually happens at about 0.7 volts. So that what this graph is showing is no reverse current. And then diode switches on with what they call forwards bias. Well, this thing needs a symbol if it's so blooming useful. We've seen the symbol for a resistor, that's easy. Then here comes the diode. Got an arrow, and there it is. The arrow shows which way the current can go. This other line is to indicate, sorry mate, no chance. Now, you can make diodes that emit light. So let's just have a look at them while we're here. Same symbol. That's the diode. But it has a circle around it. And then just to make it absolutely clear, here's the light being emitted. So this one here is a diode. And this one here is a light emitting diode. Current goes this way, and energy is converted from electrical energy into light energy. So there you have it. We started off by looking at Ohm's law and resistance, and we found a very simple relationship. But then we said, well, what happens if the temperature doesn't stay constant? And we found that if the temperature goes up, the resistance goes up. And then finally, we looked at a really weird thing called a diode, which allows current to pass only one way. And it's got a symbol that looks like this, and it's more famous nowadays in its guise as an LED. These are semiconductor devices, and they don't get hot. They mostly just do a job.